It's a great pleasure to have you all here. This is a series that was sparkled at the anniversary gathering of the ICTP-SAIFR here a couple years ago, and we decided that it would be interesting to create a forum to discuss quantum technologies that's going on in São Paulo and other places in Brazil. And ICTP board decided that it would be interesting for ICTP to host this and support it financially, logistically. So we had the first one early December last year. It was on quantum computation. Some of the faces I recognize that were here in that edition. And we are now in the second edition, which is quantum sensing. And there'll be a third one on quantum communications, and then one on quantum infrastructure. It's more like a finance, funding discussion, let's call it this way. And a last one that is already set for early August on how solid-state physics meets quantum technologies. That will be organized by Eduardo Miranda and Vitor Quito from São Carlos and Unicamp. So I will be brief here is the actual people doing the work on this, apart from ICTP, and I'd like to explicitly thank Dario Rosa, which is here, the ICTP fellow, and have been involved in organizing this since the first edition. Nathan Berkowitz, which is continuously supporting this meeting, and the whole staff of ICTP. But most importantly, the people that accept the endeavor to organize the individual meetings. Okay, so this turn will be Raul Celestrino from Federal University of São Carlos, and Sérgio Muniz from the University of São Paulo Physics Institutes in São Carlos. They actually did the hard work during vacation, get to invite everyone, set up everything, and it's really nice that they did so. I think we're going to have a fantastic meeting today, and I'll pass on for Sérgio to keep going on the presentation.
Thank you, Gustavo. Thank you all, everyone here also for being here today. Some of you had a few hours, a couple of hours at least to come here this morning, so I thank you, we appreciate that. And like the first meeting, and Gustavo mentioned, this is an informal discussion, so we will have now in the first part of the discussion, 3 presentations following a theme. So we will have Professor Varela Magalhães from University of São Paulo, São Carlos, talking about quantum sensing using atoms. Then we'll have Professor Carmen from CBPF that will talk about many things involving solid states. And then we will have José Inácio, also in another, one of the main axes, photons. And for that one, there's still some new ideas. We'll be talking about, he will be talking about quantum-inspired approaches. So this will be the first part of the presentation this morning. We will break for an early lunch with a little more time for discussions. So we'll get back here around 1:30 for... Yes, so we will not have the round table after the talks. We will have the lunch. So we will come a little early, 1:30 for the talks, for the table, the round table. And in the round table, we will have all the same presenters. By the way, this is an informal meeting, but just to keep things a little more easier for the presenters, we think that it probably is a good idea to have them talk for 30 minutes or so for their presentation. Then we'll have a little time for questions after each talk, but you can save the bigger questions if you wish for the round table later. They will be in the round table as well. And we will have other guests for the round table representing other platforms and applications. And then at that time, I'll present the other presenters. So with that, let's start with Daniel. So
that I forgot. I was advised that everyone must sign the sheet here, the present sheet, because that's how you justify the funding. So I'll ask if you haven't done it yet, please do so that we have everyone on board sign there so that. Okay.
Yes, where, no. Where we need to. The mezzanino, okay, so upstairs. I saw some posters there, okay, all right. We'll take people there. So, by the way, we are transmitting online, and so for the people that are seeing us online now, please put your questions in the chat for the ones that are connected. And we'll have somebody, I think Dario kindly will help us to look, to watch for that. So just type your questions there. Then after the talk, we'll come to them. So Daniel, first speakers for this session, and thank you very much for accepting the invitation again.
Thank you. I am here. I have no guitar, but I'll try to do with the free hands, to talk a bit with the hands too. So thanks for the organization, for the invitation, and everyone to be here and have the patience to hear me. I belong to the Institute of Physics, São Carlos Institute of Physics, and so we are 230 kilometers from here, around. And I belong to the Center of Research in Optics and Photonics that is going to be established in the university as a formal structure of the university. I think is next month, I guess. There will be the ceremony to fix this. That's a long-term project from FAPESP, and then the University of São Paulo decided to turn all these centers in and set up them in the structure of the university to have some independence for new projects and so on. So this is a long story. I will just abbreviate here. Anything you want to know, you can try to find the information in the website of the center. And if you don't find, because we are not so good in doing advertisements, normally, and the websites are very poor, and then you can write me, and it will be a pleasure to answer any questions or any points about it. Okay. When I was discussing with Sergio about this talk, I was afraid, and I'm still afraid, and I'm sure that I'm missing a lot of points on it, because we have a lot of works being done around about atoms as sensors, and to be used in, let's say, quantum 2 or quantum 1 manner. This gives a very large number of reference that can be done. And if I'm showing some things that remember maybe from where this comes from, the very beginning of the discussions, the tools that we use until nowadays, and they were supposed or proposed a long time ago. And then I tried also to have some reference that were very like last year, this year, or 2 years ago. So you can look at the reference and open the tree of the reference that they have. Some of them are reviews, and I can provide for anyone that want all the PDFs that I collected to this, that are organized in the directory for the presentation. So anything you want, that it will be a pleasure to provide. Okay. The first thing that when we discussed about the presentation is we are talking about quantum science and quantum technology. And when we talk about quantum technology, this brings a new actor sometimes to the academy. That's a lot of time is the private sector and the private interests. And then we should see some reviews and how they think about maturity of the technology that we are sometimes presenting to them, and asking them to invest in the academy to continue and to going on. Sorry. Where is this? Yeah, okay, thank you. So, exactly in the point that I was starting to use it. And so I found some reviews and general reference about collecting data for the patent filing in the last years related to quantum technologies, because it's patent, then it should be related to invention and somehow to technology. And this increased a lot in the last years. This is not, they followed a criteria. They explain in the paper, but they follow the criteria. Of course, there are a lot of patents that are missing there, but it shows that we can see the increasing interest on registering the intellectual property about quantum sensors and quantum applications, okay? I have this PDF, so if you want to just ask me. And then I found also some more recent papers about quantum technologies exploiting the quantum part of systems, or quantum part, the quantum sensing, and as I told you, exploring interference, but sometimes exploring simple spectroscopy. So this is about sensitivity, and this is about a lot of things. And what I found in some of the reviews, that's the sensing, like this one, that's provided by some Israeli guys, that they are also looking for maturity, the readiness level of the technology that are being presented. Because this is something that sometimes shows some kind of frustration on the other side. So people sometimes talk about management of frustrations, because someone expects something that is already very advanced, and then you show something that's advanced to you, but because of the result, but advanced. What's advanced in the sense of the private side or the application side? Sometimes it's not only the high stability, it's not only the high accuracy. The readiness is something more, okay? So these are some terms that I want to discuss a bit in some slides. Why we want to use atoms as reference? I stole this from some papers. I gave the reference here for the Strontium lines, and there is the another paper from our group here. But why we use this? Because they provide absolute reference. This is maybe the first discussion that and the first jokes that we can find in the group, inside the group. Because sometimes people say atoms are atoms, and an atom is an atom everywhere. Yeah, but they provide absolute reference if you know the model, if you have a good model to all the influence that the environment gives to the, or impose to the atom. Because all the transitions, we know about a lot of effects that the environment can provide and can impose to the atom, like black body radiation, like magnetic field effects that can displace the transition. And so how we can talk about absolute reference when we say we are using an atomic transition? So the first advertisement sometimes that we do is something that's not, look, until some point, an atom is an atom everywhere, and it's not going to change. It's going to change. The good point is that we believe that we know how it changes. And this is the main part of the game. How well we model all the effects that are imposing some shifts in the atomic transitions. This is the part of the game here. And another point is to find good transitions to work with. So it's not the case of using any kind of transition. What are the good transitions that we can use? These are sometimes for one of the quantities that are measured, that is time. This is called clock transition. Okay, why we call it clock? What's a good clock transition? A clock transition is a transition, an atomic transition that stays for a while. So you have some time to work with the atoms. So the lifetime of the excited state, it stays for a while. This gives place for a thinner transition, observed transition in spectroscopy, and the less sensitive to the environmental effects. Okay, this is good for sensing time, but this is not good for sensing other quantities, like magnetic fields, because you look for a clock transition or a transition that's less sensitive to magnetic field. If you want a sensor for magnetic field, it's not the same transition sometimes, not normally, okay? And then you have to find other transitions. Sometimes it's the transition that is for the Zeeman effect, is the higher transition, or a transition that gives at least first order effect for the magnetic field, for example. So you give some sensitivity. This is one of the terms I would like to point out here, and maybe challenge you to think about afterwards, okay? So the first point is to have the transition for each application. So it's not one, there is not the Saint Graal for everything. And we have, at least we have work for everyone, like. And this is the first point. Another point that I would like to point out is something that we find a lot in the papers, is about sensitivity, stability, accuracy. And I think you already know about this, but I would like to point out sometimes we see this and we confuse a bit about accuracy. You can have something that's less precise in terms of measurements, but you can integrate or do somehow more averaging time for the measurement, and you can find a very nice accuracy as a result of your measurements, okay? Sometimes you have a very nice sensor that has a lot of stability, like here, but has to be calibrated because it's very stable, but it's out of the right point. The true value, this is, I don't know how used you are to these definitions, what is a true value of a measurement and so on, but it's the expected value for the result of the measurement is not exactly at the center of the averaging that you are taking for a given measurement, okay? And this has to be taken into account when you take these measurements, because you have to see about statistical noise and systematic effects. How these effects affect the measurement that you are doing. And this is all about sensors, right? And also because there are some, well, let me talk already. This is about some influencers that we have a lot nowadays in internet, and they are talking that quantum sensing and quantum sensors are very nice because quantum systems are very sensitive to the environment, and so they are good sensors, right? No, because they are sensitive to everything. And I just want to measure magnetic field, not everything integrated in a single measurement. And so I have to be sensitive to to a given quantity and separate it from the others. This is the play or the game that we have to play every time. How to model the system, and this gives a lot of work all the colleagues will talk about these things afterwards, but and we can discuss a bit more after. But this is all the game that we have. And also, you have something that's very sensitive, and there is another term that we have to talk about, that's about dynamic range. And dynamic range means that if you have something that is 10 to minus 20, it can't saturate at 10 to minus 18, because you want to have a very long range of measurements. If it's very sensitive, but if you, for acceleration, but if you move it from here to here, you lose all the measurements. It makes no sense for quantum technologies. Then we have to think about all the applications or the applications area that you can use, okay? And when looking for all these environmental effects, we have the systematic effects. This gives place to frequency shifts. This is well observed in atomic clocks. And there is a list of some of them, like magnetic field, black body radiation. But as I told you already, for the clocks, for atomic frequency standards, we want to avoid it. We want to avoid them. So we look for transitions that minimize this kind of effects, or ways of minimizing. For sensors, for magnetic field, and BBR, black body radiation, or microwave leakage, it could be if you talk about radio frequency and microwave detection. So if you are minimizing the environmental effects, you want to avoid them, and this is not a good sensor for these clock transitions, okay? Another thing that appears a lot in the papers that sometimes not so understood as that's the Allen variance. That's a way of characterizing the set of measurements, the temporal sequence of measurements that you take, and then we see this kind of expression in the measurement, and then we should understand a bit about it. And I have to run because the time is going. And the main point that I'm going to show repeatedly from now is about this number that appears first sometimes in this tau and the minus half. So the minus half gives what is the slope that we have if we take bigger and bigger number of measurements and we take average. What is the standard deviation? We talk about Allen variance, but we represent normally the Allen standard deviation. So that's what's represented here. And if we take a bigger set of measurements, how behaves the standard deviation? So I took 10 averaging points and 10 averaging points. If I take the standard deviation of these, what's the standard deviation? Then I have 100 of each averaging result. What's this new standard deviation? This is very simple to understand afterwards, but this gives, the inclination gives a characteristic of the noise that observed in the temporal sequences of the measurements, okay? And then we have this white frequency that's the limit in the quantum systems for the standard quantum limit. So if we don't have any kind of skill to reduce this more than the standard quantum limit, we are every time. This is one of the limitations that are present in the classical sensors and the classical quantum sensors, let's say, classical way of doing the experiments, okay? And this is the stability that's shown. So just to point out again, so this is the stability that's shown at 1 second when tau is 1. So this is the very beginning. Sometimes we see some papers talking about, we have measurements in 10 to the minus 16, 10 to the minus 17, but how much integration time you have to present this kind of stability. Then we have to be critical when reading this kind of papers, because then we should compare in a fair way each result, okay? And so we see for the first quantity I'm talking about already, that's about time, we see from the years how is improving the fractional uncertainty, not the stability. So how you feel or how you model each system to talk about accuracy. So this is uncertainty. And how it is decreasing until 2020. And this is kind of minus 10 to the minus 18 already for optical clocks and so on. And this has to be updated maybe every 5 years or so on. And we see this, this is the set of microwave clocks, and this is for the optical clocks. And for the optical clocks and the uncertainty, they deal with something that's called fractional frequency 2. So this is normalized against the frequency the frequency range where you are measuring. So if I am measuring in an optical frequency, of course I start, so this normalization is 10 to minus 15 already. So if I have something that there is an error in the first decimal place of an optical frequency, I am already in 10 to the minus 16. If I have a microwave clock, a microwave system that's 9 gigahertz, so it's about 10 to minus 10. If I start in the first decimal place, so I'm 10 to the minus 11 only. So this always depends on the normalization too, okay? But it's very nice to have all these improvement in the uncertainty in the last few years. And then this is always because we have improved the quality factor of the lines that are in the spectroscopy that are observed, okay? And even from microwave clocks, from beam standards, and then with cold atoms, and also with optical domain in optical lines spectroscopy for clock transitions. And for the bunch of atoms and techniques that we have in both domains, that we can synchronize and give comparisons using frequency comb for coherent synchronization and comparisons between the two domains. This is very important too. And they bring a very old technique. A lot of them, not all of them, but they bring an old technique that I call it here Ramsey's insight, to generate coherence or superposition of states in a technique that applies, I'll talk about microwave pulse for, this is nuclear magnetic resonance that were tested by that time. This is in the 50s or even before. The Nobel lecture, it was in 1989, but he was applying separate pulses technique to improve the resolution of an observed transition. So this gives a reduction of the line width of this observed transition, but it also took another skew or something that gave the superposition of states remaining for a lot of time if you have a clock transition, if you have a transition that stays in the excited state, because if you don't have so many time to deal with, that makes no sense to apply sometimes, okay? But this gives this superposition of states, and it's also used for quantum computing nowadays and so on. Okay. But this is a very old technique. by that time, it was used to compensate for the long interrogation time that you need, but you could. It is a fundamental state transition, but if you compare with the same kind of single pulse or two pulses applications, the reduction is not so big, but because of technical limitations, you can't do it for long times or in a long length during the measurements, because then you have to reduce the microwave and the amplitude of the field so low that you are in technical noise and so on. This is because it was applied first. So the fair comparison is about this line width and the central line width in the Ramsey fringe that can reduce is about 100 times and so on. Okay, but nowadays this interference that is sometimes that's comparable with the double slit experiment, but this is about double slit experiment in time. This gives place of other applications in quantum sensing too, because you are for a long time not evolving in the Rabi oscillation, but you are for a lot of time you are within a superposition of states that if it's disturbed, you create a disturbance in the interference fringe too. So you can see this as a signature of the Ramsey in the Ramsey fringe of the system, the superposed states, and then if something disturbs these states, then you can look after and see how this can be interpreted as a kind of a quantity that is evolving or changing somehow. Okay, and this is used. This is another review, and this is used a lot for quantum sensing. And I am going fastly to just give this tons of applications. Like the actual sensors, let's say for time, we still have the Ramsey method being applied in atomic fountains. And then we have this kind of stability at 10 to the minus 14 at 1 second. But after 10,000 seconds, you integrate below 10 to minus 16. We have some optical transitions being measured, and we have these last results from Jun-Ye in 2024, claiming for uncertainty about 10 to minus 19. This is amazing, but this is uncertainty, and I just ask for attention here because we have here in this paper uncertainty, not stability, and this is calculated because every systematic effect has an uncertainty of being characterized, and then this provides an uncertainty of the result, okay? This is not the frequency shift itself, but the uncertainty about the frequency shift that gives the uncertainty of the whole system. And then we have this set of measurements done between a consortium of European laboratories, like strontium and mercury, strontium and terbium ion, and so on, that are giving, in fact, after 10,000 measurements, or almost 10 to the 5, almost 10 to minus 17, but it's starting, all of them starting at 10 to the minus 15, more or less, okay? But of course, when you talk about stability, you talk about this decrease limited by the quantum standard quantum limit, and then it decreases with tau to the minus 1/2, and then it decreases after 2 orders of magnitude. It decreases easily after 1,000 seconds. But when we talk about this with sensors, for example, I'll show another results for sensors, but when we talk about a resolution or a sensitivity or a stability of 10 to the minus 18 or minus 10 in magnetic field, in gravity, for example, And then we talk for someone that wants to have a product. He says, okay, very nice. Let's put it in a submarine and make it an embedded system. That, no, this is after 10,000 seconds. So you have to stay steady more than 1 hour, integrating and integrating to have this resolution. So we have to be very careful when talking about this kind of results to provide the good ones, even or the real ones, or the applicable ones, instead of the more impressive here. But of course, if we are measuring something that can be steady, like the gravity field surrounding an experiment sometimes, and then you can integrate, okay, that's not a problem. But it's not only talking about the number, but all the context that you have, okay? For other quantities, we have a lot of results too. I took only some of them. There are some private companies also with gravimeters, and they are doing some surveying about gravity in volcans and measuring some geodesical characteristics of some environments too. And we have this modification of the Ramsey method. I'm not going into the details because we have no time, but we have the superposition of states, but with an additional step to have atomic interferometry. And then this gives to the system the sensitivity to gravity that we don't have only observing the clock transition with the traditional Ramsey method. And this gives the step in the direction of giving that sensitivity that I told you before, that I want to have only for the gravity, for gravity, okay? And then I can, and only for acceleration, this is for static acceleration, and then we can have these, this is 10 to 2, so this is 100, but this is in nanometers per second. This is, the scale is 10 to the minus 9. And it decreases down to 1, so this is 10 to minus 9 meters per square second, okay? So it's the measurement that they have. And this is kind of almost the state of the art with these interferometers nowadays. So they decreased it a bit. They improved a bit accuracy, and like here. So this E is the nanometer per second, the scale that they have. So they can go to the 10 to the minus 1, so decreased 1 decade already. And this is doing a differential. So they have 2 gravimeters here. So they produce 2 thermal clouds of, I think it's cesium atoms. I'm not sure they are doing this with rubidium or cesium. I don't remember now. But they produce 2 thermal clouds. Thermal clouds is because of the Bose-Einstein condensate gas. They call atoms in microkelvin thermal clouds, thermal atoms. So they are not cold enough to them, so they talk about this. But this is cold atoms clouds that fall with the gravity. They experiment the 3 pulses to have the atom interferometer, and then you have the result that's sensitive to gravity, okay? This is another adaptation of the experiment. That's the same experiment doing the 3 pulses, but in different directions. So you can measure acceleration in different directions too. So that's what I was talking about, the applications or what we want to. This is a more steady measurement that you have to stay somewhere measuring gravity, but here people want to measure 3D acceleration. So what are the components of the acceleration? So they prepared the atom interferometer with different components to calculate acceleration in different axes, okay? So this is already being done. This is the test in the inertial platform that tilts the system and measure against different inclinations, and that's what they do. So the island deviation, this is for stability, and they have already, but it's GA. This is not nanometers. So this is already 10 to minus 4. So it's not so good as in the previous case of gravity. Okay, but it's already quite impressive to see systems that are being prepared to another kind of applications. As I told already, depending on the applications, you don't have to be in the limit of in the state of the art of the steady measurement. It's enough to have something like this. Another variation of the three pulses of the atom interferometer is to launch against a given direction, and then you take differential measurements in one sense and the other, and then you can talk about angular speed in a given direction. And then you have a gyroscope, an atomic gyroscope. This belongs to the same group. But this is a bit big, let's say. It's an experiment about 1 meter tall. So you talk about gyroscopes being employed in airships. That has to be that has to have a volume much smaller, like a laser gyroscope or even fiber gyroscopes. And then what people are doing too is trying to have a direct measurement of angular speed direct in the cold cloud. It's not a Bose-Einstein condensate, it's a simple thermal cloud. In almost free fall, because it's in the very beginning, but then if you have an acceleration, you see in the results some fringes, and then you take the measurement of the fringe, and they can estimate the angular rotation of the experiment. So they applied doing some measurements, tilting the system and so on. This is from NIST. Elizabeth Donnelly is doing this more recently, and I don't see other publication afterwards, but I hope they are evolving on this. Because the results starting, they were not so impressive in comparison with the other gyroscopes. Of course, they are much more, they evolved much more. They have a lot of time more than them, but this is something that can be reduced in volume a lot, and this is very nice to have the perspective. The limitations, just to go to the end nowadays, are about two effects that are very old, in fact. These two effects are about something called sensitivity function and Dicke effect. It's not the Dicke effect for the cavity and the atoms. This is another thing. The Dicke effect is something from 1987 that was pointed out by John Dicke. And this is because you have a lot of preparation of the system, of the atomic ensemble, to be interrogated, like in a clock, like in another sensor. And all this is not under the superposition of states. So preparing the experiment, then you launch for sensing something, some quantity. And only when you have the superposition of states is the time interval where you have really the sensitive system for your application. So you don't have a full time interrogating the atoms. So this gives place to some limitations, and John Dicke gave some insights about this, because you have the sensitivity of the superposed states here, but all this cycle time, you are not sensitive to any kind of variation in the system. So the system around the environment, let's say, is free evolving, and you know nothing about it with the atoms, okay? And this gives some limitations. If you decrease these, and then you can evolve with a double pulse technique to increase the sensitivity that you have. This is the sensitivity function that you have for a single pulse system, and this for the double pulse. Why is this? This is very simple. In fact, if you think about the Rabi oscillation, that's a sinusoidal form. This is the derivative of the sinusoidal form. So you have the maximum sensitivity when your superposition of states is in the middle. So you have maximum derivative. So you are in the most sensitive part of it. In the Ramsey method, you evolve with pi over 2 pulse. You evolve for this half height in the superposition of states. And then you go to the maximum sensitivity for a longer time, and then you come down because you continue the Rabi oscillation, okay? The half of the pi pulse in the Rabi oscillation. So how people are addressing this? They are addressing all these kind of limitations in the standard quantum limiting, trying to have techniques like squeezed states and quantum non-demolition measurements. So with quantum non-demolition measurements, you decrease the dead time where you prepare your system, so you minimize this Dicke effect. So you are almost every time evolving in the measurement and sensing the system and sensing the environment. And also with spin squeezing, you limit something. In the original papers, in the first papers of Norman Ramsey, he discusses a bit about the spread of phase in the atomic system, starting in with the double pulse experiment. But it's interesting because then he gets rid of it because he says this is eliminated because we have some symmetry in the interrogation, and then we get rid of it. But when we use squeezed states, we can go even below the standard quantum limit, and this is what people are doing now. And this is what people propose in here. I think Philippe will talk a bit about this later. But this is about testing an atomic ensemble inside a cavity, an optical cavity, and then you can produce this. This is a proposition. It's not from 2015. It's even earlier. It's like 13, right, Philippe? Yeah, but yeah, okay. But then this is something that gives you some squeezing of the states, and then you surpasses the quantum limit with this. You can surpass it. And then we have some indications with some papers that did some observation of atoms inside cavities, and they are seeing some improvement. Still, if they are not below the quantum this standard quantum limit, okay? Here, there's another paper that improved a bit. It's still not below the standard quantum limit, but some measurements that are already showing some experimental results going below this standard quantum limit. Because what is this is just to not have the decrease in the stability of tau 2 minus 1/2, but tau 2 minus 1, and then if you average more, you can go below much faster, okay? So this is much about giving some results to you. You can have all these reference here, and what's the state of the art at the very end of the last slides. And then you can find some other reference in these papers too. We are still evolving. We have a lot of impressive results, and but This clock operation here, it's about 10 to minus 16, but it's still, this is 10 seconds of averaging. Or if you integrate up to 10,000, then or 1,000 decrease 1 or 2 other order of magnitude, and then it should be much better. Okay, so this gives a general view about the techniques and about atomic sensors, and I hope you enjoy if you try to find out some more reference and so on. Thank you very much.
Thank you, Daniel, for this very nice introduction about quantum sensing with cold atoms and cold atoms, let's say, not just cold atoms. So I will now ask if you have some questions. I will also remember that we have a discussion in the afternoon, so keep some for the afternoon, but maybe we let 1 or 2 from the audience if you have now. Yes?
Maybe a very naive question. If I understand correctly, in the talk you presented all the experimental challenges. Are there theoretical challenges as well, or is super well under control?
I think they're still under control because, of course, the perspective or the prospects are much better than you have in the experimental observations. But maybe to understand better some limitations, even the experiments, we should improve better in the modeling. Yeah. But of course, if you take from some theoreticians, some papers too, you see that the predicted noise it's much below, and so you can find the Heisenberg limit. Because, of course, they always deal with some experimental results and some real characteristics to apply the models already.
Are there any questions at the chat? No? Okay.
We can announce if they have questions.
Yes, so if people at home...
Yeah, I mean, people in the chat, do they have questions?
Yes, okay, they can send. Otherwise, are there any questions in the audience? Yes?
Thank you for the talk. I'm just curious of what are there any initiatives here in Brazil on trying to decrease the size of these experiments on atomic physics? Because, of course, as you show, there are examples using just vapor cells of 1 centimeter. Of course, the signals and the coherences are way less comparative to what you can get with cold atoms. But I know that there are some groups outside that they are working on trying to bring the size of the cold atom system to be competitive with these kind of sizes and actually try to make them like more commerciable in the sense of trying to do this kind of sensors miniaturized. So is there any initiative on trying to decrease the size?
I'd say yes. There are some, at least part of the system, maybe part of the critical, some of the critical parts, like cavity or like some parts of reference that are critical, because if you have a volumetric system, if you go to an embedded application, then you don't succeed, it's not possible. And there are some, but of course you need a lot of investment in infrastructure also to do this. This is more engineering work to reduce with some confidence that you don't lose a lot of stability and you add a lot of noise and so on. So this compromise, this kind of system engineering and takes a while. Like in the techniques they show you, the Ramsey method is from the 50s, even the 40s, to start to be shown something, to show something. And if you see the time that took to have the first commercial clocks, commercial in the sense of rackable systems, it took a while. And so the challenge is here. So the cost benefit of having like something, of course, if you have a cavity, if you have very cold atoms, how many wavelengths you have to deal. And so sometimes you see this kind of system that's already meter size. It takes a lot of investment. It's not something that you solve in the, I would say, the workshop, the atelier, in the garage.
Thank you. So I think we'll let the other questions for the discussion. So I would like to thank Daniel again. And let's pass to our second speaker, Carmen Gilardoni, please.